If you really want to get into electronics, you've got to learn to speak the language. And honestly, that language boils down to just three fundamental measurements: voltage, current, and resistance. Getting these right is the key to, well, everything, from designing a new gadget to figuring out why one's on the fritz. So if you're gearing up for an exam, or you just want to get these basics down cold, you are in exactly the right place. Let's dive.
So here's how we're going to break it down. First, and this is super important, we'll talk about why accuracy is the bedrock of everything we do. Then we'll hit the big three: voltage, current, and resistance. After that, we'll take a quick peek at two energy storage concepts. And then we'll wrap it all up with a quick-fire recap and a practice question to make sure it all sticks. Let's get to it.
Okay, first things first. Before we can even think about measuring anything, we have to be able to trust our tools. I mean, think about it. If your multimeter is spitting out the wrong numbers, then every single conclusion you make from that point on is built on a shaky foundation. You're not just going to fail to fix the problem, you could end up making things a whole lot worse.
Which, brings us to this really crucial question. You pick up a meter, you take a reading, how do you actually know that number on the screen is the real deal? Are you just supposed to cross your fingers and hope for the best? No way. There's a whole system designed to prevent that.
And that system is called the Metrology Calibration Program, or METCAL for short. This slide shows the idea perfectly. Think of it like a pyramid of accuracy. Way up at the very top, you've got the national standards. These are the ultimate, undisputed sources of truth for measurement. That top standard is then used to calibrate the gear in the labs on the next level down, which in turn calibrate the labs below them. This creates an unbroken chain, so the multimeter in your hand way down at the bottom has its accuracy guaranteed all the way back up to that single source of truth at the top.
All right, so now that we know we can trust our meters, let's take our first measurement. We're going to start with voltage. And the absolute best way to think about voltage is to picture it as electrical pressure. It's the push, the force that gets things moving inside a circuit.
So the textbook definition is the potential difference between 2 points. But let's stick with our analogy. If a wire is a water pipe, voltage is the water pressure inside that pipe. The higher the pressure, the more force you have to push the water, or in our case, to push the electrons through the wire.
So why should you care about this pressure? Well, when it comes to troubleshooting, it's pretty much everything. Let's say a schematic, the circuit's blueprint, tells you there should be exactly 5 volts at a certain spot. If you measure it and you're only getting 2 volts, boom, you've just found a massive clue about what's wrong. It's how you check if a power supply is working right or if a sensitive part is getting the juice it needs to operate safely.
For the longest time, technicians use these old-school analog meters, like the one on the left. They get the job done, sure, but you have to squint and try to figure out exactly where that little needle is pointing on a busy scale. The modern digital multimeters on the right just take all that guesswork out of the equation. They give you a plain, simple number, which slashes the chance for human error and makes your measurements way more accurate.
Now, this is a really important rule to remember, so listen up. Anytime you connect a meter to a circuit, you are technically changing that circuit a tiny bit. The trick is to change it as little as possible. And to do that, your meter needs to have a super high internal resistance. We call it input impedance. The rule of thumb, and it's a good one, is the 10-to-1 rule. Your meter's impedance needs to be at least 10 times higher than the circuit's impedance. This basically makes your meter invisible to the circuit, so you get a true reading of what's really going on.
And speaking of errors, here's a classic one that only happens with those old analog meters. It's called parallax. It's just a simple optical illusion. If you look at the needle from the side instead of straight on, it's going to look like it's pointing to a different number on the scale. It sounds simple, but it can throw your reading way off if you're not careful. Okay, let's keep building on this. If voltage is the pressure, what does that pressure do? It causes a flow. And that flow is what we call current. The pressure from the voltage makes the electrons move, and the rate of that movement, well, that's the current.
To put it simply, current is just a count of how many electrons are flowing past a specific point in 1 second. We measure this flow in a unit called amperes, or as everyone calls them, amps.
Now, measuring current is totally different from measuring voltage. To measure the flow of water in a pipe, you can't just look at it. You have to put a flow meter inside the pipe. Same deal here. You have to physically break the circuit and stick your ammeter in there so the current flows through it. And the most important step here, without a doubt, is the first one. Always, always kill the power to the circuit before you start messing with it.
Because, let's be honest, breaking open a circuit can be a real pain, and sometimes it's just not safe. Thankfully, there's a much cooler tool for the job, a current probe. This thing just clamps right around the outside of the wire. It works by sensing the tiny magnetic field that gets created anytime current flows through a wire. It's totally non-invasive, it's a lot safer, and it's way, way more convenient.
Okay, so we've got our pressure, that's voltage, and we've got our flow, that's current. So what's left? Well, something has to control that flow, right? There's an opposition to the flow, and that, my friends, is resistance. It's the thing that limits how much current can flow for any given amount of voltage.
Pretty much every single component in the circuit has some amount of resistance, which we measure in ohms. Going back to our water pipe, you can think of resistance as a narrow, pinched section in the pipe. It just makes it harder for the water to get through. Okay, I really need you to listen to this. This is the single most important rule when you're measuring resistance. You absolutely must remove all power from the circuit first. No exceptions. And here's why. Your ohm meter has its own little batteries inside, and it works by sending its own tiny current through the component to measure it. If you connect it to a circuit that's already powered up, you're going to send all that external voltage flooding back into your meter, and you will almost certainly fry it.
All right, let's quickly touch on two slightly more advanced ideas. So far, we've talked about resistors, which get rid of energy as heat. But there are also components that are all about storing energy, capacitors and inductors. And this slide lays out the difference perfectly. Capacitors store energy in an electric field. You can almost think of them like tiny, super-fast rechargeable batteries, and because of that, they tend to fight against any changes in voltage. Inductors, on the other hand, store their energy in a magnetic field, and they fight against any changes in current. They're really like two sides of the same energy-storing coin. They just react to changes in the circuit in opposite ways.
And this brings us to our final and maybe the most important safety rule of all. Because capacitors are so good at storing energy, they can hold on to it like a charged battery, even long after you've unplugged the main power. A big capacitor can store a deadly amount of charge. So, before you ever work on a circuit with large capacitors, you have to make sure you've safely discharged them first. Seriously, no exceptions.
Wow, okay. We have covered a ton of ground, from the very foundation of accuracy to the core measurements and those critical safety rules. So, before we wrap this up, let's do a quick review to really lock in these key concepts, especially if you've got an exam coming up. All right, let's do a rapid-fire round. Metcal, that's the system that guarantees your gear is accurate. Voltage, electrical pressure. Current, electrical flow. Resistance, the opposition to that flow. Input impedance, that's what keeps your meter from messing with the circuit. And parallax, that's the viewing angle error you get with the old analog meters. Okay, ready to put that to the test?
All right, time for a pop quiz. This question comes straight from the source material. What is the one thing that assures the accuracy of your electronic test equipment? Think about it for a second.
And the answer is, it's calibration. See, it all comes back to that very first thing we talked about. That unbroken chain of accuracy in the Metcal program is what lets you trust every single measurement you take. If you can master these fundamentals, you are going to have a rock-solid foundation for anything you do in electronics. Thanks for tuning in.